Hello, everyone. My name is Patrick Rebeschini, Associate Professor in the Department of Statistics at the University of Oxford. So the goal of this video is that of introducing you to the field of statistics, taking machine learning as a running example to show you really how statistical thinking permeates much of the technology that is driving our modern society. I hope to be able to convince you that the way you have been exposed to statistics throughout your A-level, high school, more in general, is by no means representative of what we do as statisticians. So you might have the feeling that statistics is about applying, perhaps rather mechanically, formulas in order to solve problems. Well, here, as statistician, what we are really trying to do is we try to understand this formula fundamentally, to derive them, and to use them to capture and perhaps more importantly, exploit the science of data, the science of randomness, which is what statistics is about. So in the process of doing so, I've actually decided throughout this talk to introduce you to some of the main ideas that we teach to our undergraduate at Oxford, so you have a glimpse of what this degree is about. But before we get there, let's begin with our running example, machine learning. So up to, well, not that many years ago, 5-10 years ago, machine learning was really associated with some robots trying to conquer the world. These days, it's well known that this field, this technology is behind the scenes in a variety of application and services that we use routinely, from search engine, voice recognitions, and so on and so forth. And in particular, is machine learning is behind a revolution that is currently happening in the field of games. So here, what I'm showing you is one of the many examples you can find online of an algorithm, a bot, that automatically learns how to play, in this case, Mario Bros. So the algorithm starts from scratch without knowing how to play the game. The only thing that we input as part of the algorithm are the rules of the games and a notion of rewards, here in this case, perhaps associated with the time Mario Bros can stay alive before dying. And through a setting of episodes and repetition of the game, the data gather the algorithm generates data and uses them in order to fine-tune the action to be performed in order to, well, maximize the notion of reward. And here you see what happens after a few iterations of this game. This is what happened after a few thousands iteration of the game, and you clearly see how Mario Bros has learned how to stay alive and eventually complete the level. So appreciate, once again, we are not hard inputting what Mario Bros should do. We are just designing the system, telling the rules of the game, and establishing a notion of rewards. So, of course, you might not like the idea of coming to Oxford to design video games. Some of you might, but the truth is that video games is just one example of a fundamental playground that is nowadays used for a variety of application of interest. Video games gives you close control on the system in front of you. And in fact, there are many things that you might think to do with it. For instance, if you played Grand Theft Auto, this is a video game where apparently you are in a city and you can steal cars and drive around, where that video game has been used by scientists in order to generate the data to train a self-driving car to be eventually deployed in the real world. The point being is that in a video game, you have full control on the state of the weather, so you can choose to generate data involving snow or sun without necessarily waiting for these two things, sun as well, happening in Oxford. Okay, but so let's take this video games idea, and this is something I want to focus on in the setting of a particular game, which is related to the so-called Multiarm Bandits problem. So the game can be easily phrased as follows. Suppose you go to Las Vegas, and you're given a choice of multiple slot machine, in this case, 2 of them, and you need to decide which one to pick. So you perform a game that evolves with time, an iterative game. At each time step, you get to choose between 2 or, in general, many machines. So the name one-arm bandit refers to a one-slot machine. They steal your money, right? They're bandits. Multi-arms multi-arm bandits refer to the fact that you have multiple slot machines. And here, what you see on the right actually is the first slot machine that was ever designed about, well, 100 years ago, a bit more in the US. Liberty Bell. One of the 5 things you could get by playing this slot machine along with horseshoes was in fact a representation of the Liberty Bell, which is, well, one of the main symbols of American independence in Philadelphia. So where is statistics, right? So I just phrased the problem, which slot machine to pick. In order for the problem to be well posed, of course, we need to make some assumption in order to solve it. So the assumption we are going to make are the following. We assume that each slot machine is associated with a certain unknown distribution behind the scene. So think of each slot machine as being a coin, for instance. And each coin, each of these slot machine has a certain bias of giving you a reward, perhaps more towards 1, which is, say, something good for us, or a reward close to 0, something bad for us, with a certain probability, okay? And from our point of view, well, we model this slot machine as encoding random distribution, coin flips, if you want, but we don't know the bias of each coin flip, and that's what we are after figuring out. Okay, so statistically, statistics fundamentally enter in the assumptions we are making about the problem and in the way we encode the randomness. Okay, and here we are in a situation much like Mario Bros, where there is a learner, us, that we play a sequence of action, choosing slot machines. We interact with an environment. In this case, well, we get a rewards from an environment. We don't impact the environment, as in the case of Mario Bros. An action in Mario Bros was making the screen, giving you a different disposition of pixels, so the environment itself was changing. Here in the simpler setting of the multi-arm bandit problem, we are just getting rewards from the environment, but we are not impacting the environment. We don't change the distribution of the slot machine. Anyway, by playing action, we get rewards, and we use this reward in order to fine-tune our policy. Okay? We generate data this way, and we aim to learn from this data. So what is one of the main type of policy that might come to mind when you play this type of game? Let's introduce it as follows. So say that we are dealing with a setting with 2 slot machine, which I'm calling arm 1 and arm 2. And we play this game as indexed by time. And at each time step, we get to pick 1 slot machine. Say time step 1, by default, we pick arm 2. We get this reward, which is something close to 0, so bad for us. And at time step 2, we get, by default, we play arm 1, and we get this reward from arm 1, which is in this axis, well, something closer to 1, so something better for us. Now, if I were to ask you which slot machine will you play next, I'm pretty sure your answer will be, well, let's play arm 1 again, right? You're implicitly thinking as a statistician, you're using the data in front of you as a minimal form of data, just 1 data point per arm, and you're saying, okay, let's look at right the level of this reward here represented by these horizontal bars, red bars, and I'm observing that, well, the reward I'm getting from R1 is better than the reward I'm getting from R2, and so right, this tells me, okay, let's pick R1 again for the next step. And let's assume that I'm doing that and I get this reward, and I ask you the same question, which slot machine will you play next? And my guess is that you will implicitly, again, put in your hat of a statistician, and you will be thinking the following terms. You will be thinking, okay, now I have 2 arms, 2 rewards from arm 1. I can take the average of them, the so-called running mean, sample mean, and compare the average now of the rewards. And in this case, well, we are still in a situation where the average of a reward is more favorable for arm 1. And so we are, if we follow this policy, we'll be picking arm 1 again. And yeah, this is just a situation where I keep using this policy. I keep computing the running mean to play this game. And of course, well, you might very well ask, okay, is this ideal, right? Afterward, by using this policy in this particular example, at least, we have been stuck with playing arm 1. Could have been the case that arm 2, in fact, was better the distribution behind the scene was better for ARM2, and we were just unlucky at the very beginning. And this is what is happening in this representation here. Here you see I'm writing the histogram that encodes the distribution associated to the two arms. So the length of the blue bar represented the probability of having a certain type of rewards. So for ARM1, for instance, we were having a bigger probability of having a reward closer to 0 and a smaller probability of having a reward closer to 1, which is what we observe from our samples if we play ARM1. And we see that, well, ARM2 actually had a very small probability of getting a reward close to 0, which is what we obtained in the first time step. We were very unlucky. And there was the reason that is behind the scene is unknown to us, a very big probability of getting a reward closer, much closer to 1. Okay, so in fact, these are the two distributions. Again, think of them as the probability of having certain outcome from coin flips. And if I were to compute the so-called population mean of this unknown distribution, we will be here in a situation where the population mean of ARM2 is better. And so, right, under this notion of what it means for an ARM to be better than the other, here we are in a setting where ARM2 is better, but the policy we have been following is such that we were unlucky and we ended up playing ARM1. And the main reason why we, why this is a bad policy at the end of the day is that it's just based on the sample mean. And as such, we are just exploiting the information we have at our disposal by playing these arms. As we're going to see, a key way to get around this problem is that of using statistics in order to design a modification of the algorithm I just exposed to you, so to introduce notion of exploration, not just exploitation. And this gives me really the opportunity to speak more in general about statistics and the field and what we care about. And so here, let's look at the following case where, again, there is a certain distribution behind the scene, which is unknown to us. In this case, say a coin flip, where with 10% probability, the coin gives you a 0 reward and 90% probability gives you a reward equal to 1. And right, there is someone, say Tiki, which is the Greek goddess of luck. Someone has chosen this distribution, has given us this coin with a certain bias, but the bias is unknown. And as statistician to us, and as statistician, what we care about, well, is trying to figure out properties of this unknown so-called population distribution using data that we can generate from it. Okay. In particular, in this example of bandits, we care about figuring out the population mean, which is here given by what? 0 times 10% plus 1 times 90%, so 0.9. This is the parameter we want to figure out. And well, and this is a representation of Tyche. This is a Roman copy of the original Greek sculpture. The Roman version of Tyche is Der Fortuna. All right, so here's the setup. So there is the population side of the word, something that only God knows. And as statistician, we can get samples, we can flip the coin, and we can perform experiments such as flipping the same coin independently for n times. As a result of this experiment, well, we can compute the sample mean. We can take the average of the data we have in front of us. This is what we have been doing in the bandits example, and say that we get 0.7. And we are then faced with, we are now implicitly designing an estimator to well, estimate the unknown population mean. And in a snapshot, in one slide, this is what statistics is about, using data to gather information about unknown distributions. Now, the sample mean is a point estimate. So the 0.7 is a point, is a number. And the first thing that we teach at Oxford is how to design point estimator using the general framework of maximum likelihood that you might have heard of. But the second thing we teach at Oxford is how to use this general framework of statistics to actually encode notion of errors about this point estimate. So 0.7 per se doesn't tell us much, right? How can we be sure that 0.7 is close to the unknown parameter that we would like to infer, which is 0.9? And that's where a notion of the quality of the estimator comes into play through these confidence interval ideas. So in order to introduce confidence interval, which is again the second main thing that we teach at Oxford in the first year of your undergraduate degree in the Math and Stats curriculum, in order to introduce this idea of the quality of estimator, I want you to think of performing the same experiment I've done before, namely taking this coin and flipping it n time step. Let's perform this same experiment more than once. Okay, so if I perform the experiment once, I get a certain sample mean. If I perform the experiment twice, again, independently, I keep flipping the coin for another set of n time steps, I get another sample mean as a result of the second experiment. And I can do this, I can repeat this same experiment independently for, say, m times. Okay, so now there are these two parameters I want you to focus on. N is the sample size, is the number of time steps we flip a coin in each experiment. And m is the number of experiments we are performing. As a result of this m experiment, we have m sample means. And so we can, plot them together. And well, the question is, what can we do with this piece of information in order to try to get an estimator and a quality of an estimator for the true unknown population mean? And the procedure is fairly simple. We take these m outcomes of these m experiments. We divide the interval into bins, equally spaced, and we create the frequency histogram. We just count the number of sample means from these experiments that land in each specific bin. We end up with an histogram, and now there is the natural, the question is, what can we do with this histogram in order to, again, estimate the population mean behind the scene that is unknown to us? And the way to get there is to, well, look at what happens when we increase the number of experiment m that we are performing. So what I'm showing you now is an output of an experiment I perform using R, which is the main programming language that we teach in the statistics department. Here we see the case of m equal 100. So we perform 100 of this experiment, and we get this frequency histogram. And if we increase the number of experiments to 1,000, the following happens. And if we increase number of experiments to 10,000, the following happens. So you see this histogram, this frequency histogram is converging, and this can be formalized to a certain curve, a famous bell curve called the Gaussian distribution, also the normal distribution, such is of paramount importance in statistics. It's called normal distribution, which, I'm here plotting in blue. There are two key things I want to emphasize about this distribution, this curve parameterized by x. One thing is that this curve is centered around the parameter mu here in this formula, and mu in the limits of an infinitely many experiment, when m goes to infinity and we converge, the histogram converges to this blue curve, the mean of this blue curve, the point at which the curve is symmetric, the center of this curve, the mode, also called, corresponds precisely to the population mean. Okay, so this is saying, look, if you repeat this experiment for an infinite amount of time, this blue curve will be centered precisely around the true unknown population mean. So in other words, if we were able to perform infinitely many experiments, we could have access precisely to an information that only God knows about. Okay, but not just that. The other parameter that is of interest in this formula, along with mu, the mean, is given by the sigma, which encodes the standard deviation, so-called, of this curve, and is associated with the notion of width. It can be characterized, so you take the point where the curve starts from being convex to being concave, and you take the width from that point in the curve to the center of the distribution. And this is the standard deviation. And the important thing I want to characterize is that, again, in the limit of m, the number of experiments going to infinity, we have precisely this curve. The frequency histogram converges to this curve. And now this notion of width of error scales as 1 over the square root of n, where n, I recall you, is the sample size, the number of coin flips per experiment. And so this is fundamental characteristics, the fact that the standard deviation, which you can think of as notion of error, and I'm going to qualify in a second, scale as 1 over the sample size n. So this tells you in particular that if you were to, if you want to improve the quality of your estimator by a factor k, you need to take k square more data points, okay? So in this case, k is equal to 2. If you want your standard deviation, your error to be half of what we had before, you don't simply need twice as many data points, you need 4 times as many data points. And this, by the way, was a striking fact. When it was first discovered about 400 years ago, there were astronomers looking at the sky, gathering data. They had at that point access to Newtonian mechanics. So they had a model about the evolution, to predict the evolution of this planet. And right, the fundamental question back then and throughout really is, okay, if I want to predict, to get, say, k better accuracy out of my model, how many more data points do I need to take? And when it was discovered that you need k squared data points instead of simply k data points more, well, that was striking. And throughout, really, statistics has been faced with these fundamental ideas of understanding how many data points do I need in order to prescribe a certain level of accuracy. And this square root, this quadratic behavior is fundamental in many applications, precisely because of this universality phenomenon and convergence towards the Gaussian distribution that I'm describing here. There are settings, of course, where we can do better, and we can get as close as the so-called fast rate machine learning application of this. That's the terminology we use. But we need to exploit more information, more assumptions in order to get there. So anyway, long story short, we can go back to our simple setting. We have a certain point estimate, 0.7. Now we can use this whole idea of a universality, a convergence towards a Gaussian distribution. This is what we teach in the first year at Oxford, in order to introduce a notion of confidence interval. So namely what we are doing, we pick this sample mean, 0.7, and we add, in this case, it's a two-sided interval. So we add plus a certain factor and minus a certain factor. So to create this red interval, which we call confidence interval. And the interpretation of this confidence interval is as follows. If we get, again, the output of a single experiment, we create the confidence interval. The interpretation is that if we were to repeat the experiment for, say, 100 times, each time we will have a different sample mean, right? A different green bar. And the confidence interval that we can attach to each sample mean will be such that 95% of the time, the confidence interval, the red bar, will include the unknown population mean. Okay, so here we are making a qualitative step forward. It's not just having access to a point estimate. This green line is really having access to a notion of error that we can use in order to reliably say, look, within we perform the experiment once, we create this, again, confidence interval where C is a constant that is very explicit. So for a 95% confidence interval, C is equal to 1.996, close to 2, right? So depending on the number of data points, the coin flip that we have, we can create explicitly this confidence interval, and we are able to say, look, with this confidence, say 95%, we know that the unknown population mean is guaranteed to be in this interval. Okay, back to bandits. So how can we use this piece of information coming from the general theory of statistics in order to design an algorithm, modify the policy I previously described in order to get better results. So this is what we have done before. We were only exploiting. We had an algorithm based on the sample mean, which I'm going to quickly recall you about. It's just looking the algorithm we introduced before. We're just looking at the running sample mean as a way to assess which empirically, given the data at your disposal, which slot machine is better. And we ended up in this bad situation where this policy could not pick up this example, at least the best arm. And so what we can do, we can now enforce exploration using this idea of confidence interval. And so this is the policy that we're going to follow now. Well, by default, time step 1, we pick arm 2, time step 2, we pick arm 1 as before. Now we look at the sample mean as before, but what we are doing now, we are attaching the confidence interval, just the upper part of it. Okay. Previously, I told you about the two-sided confidence interval, but depending on the application, we might just want to look at a one-sided confidence interval. This is what we're doing now. We take the sample mean, the horizontal bars here in blue, and we attach to it the upper part of the confidence interval. And this red bar that we are appending on top of the sample mean scales as C, this constant I told you about before, 1.96, divided by the square root of the number of data that we have per each slot machine. Now, by this point in the game, we have played each slot machine only once. So there is a square root of 1 there, the denominator. But this is going to change. So as before, now what we're doing, we're not comparing the sample mean, we are comparing the red bar that represent the upper confidence. And the upper confidence of the first arm is greater than the upper confidence of the second arm. So as in the previous case, in fact, we are still, right, this policy still prescribes to play arm 1, which is what we are doing. But now you see immediately what is changing. So here we compute the sample mean for arm 1, but now we are appending an upper confidence bound that is smaller than before. Why? Because we have more data at our disposal coming from R1. And so here's the main idea that, right, directly coming from statistical thinking, this is the main idea that we are exploiting, the fact that more access to more data should give you more confidence to where the unknown population mean in this case lies. And we are exploiting this type of information to design an algorithm. And so as before, we are comparing the upper confidence bound. So yet again, we play R1 at the next time step. But at this point, the situation changes because once we append the upper confidence interval, now is a much smaller quantity, right? Because we have, well, it scales with the square root of n. So the decay is low if you want. It's not like scaling as 1 over n, as I mentioned before. But still, we are now in a situation where the policy, if you compare the upper limit of this confidence bound, is such that we are now prescribed to play arm 2. And at this point, the algorithm prescribes a swap. We play arm 2, and okay, we follow on this procedure. And what we can actually show is that the algorithm I just introduced to you, which goes under the name of upper confidence bound, UCB, for obvious reasons, is in fact optimal in some precise setting. So in some general setting, we cannot do better, okay? And this has application in a variety of domains. I've chosen this game setup of choosing slot machines, but I could have equivalently started off by focusing on the problem of clinical trials. So say you are a doctor and you want to perform this adaptive clinical trial by which you want to try to figure out which medicine is better. And you have a stream of patients that comes to your clinic, and each patient you are dealing with can be thought of as a time step in this game. And at each time step, per each patient, you have the choice of 1 or 2 or many, right, medicines to give to the patient. And in this way, by performing this adaptive clinical trial, following exactly the same UCB paradigm, for instance, you can figure out which medicine is better. Many other applications, these are just fictional examples. I don't think Amazon ever played with this blue color for the basket button. Anyway, this is what companies do. So every time, right, we go to a website, we are part of an experiment, many experiments, in fact. And these companies, they try to optimize a certain notion of rewards, for instance, associated to click rates or the time we spend on their platform. And at each time that we go to their website, from their point of view, it is as if they can get to pick a slot machine, right, and choose which action to perform, namely, for instance, which version of their website to show us in order to maximize their notion of reward. And again, this type of UCB algorithms are used for recommender system in order to show you movies you might like. So to optimize, again, notional rewards, right, likely associated with the time we spend on this streaming platform, or the time we spend on reading news, which is perhaps more scaring, or price dynamics. It has long been the case that if you were an owner of an Apple computer, you were more likely to be shown higher price points for the same product, as opposed to looking at the same product using a Linux or a Windows machine. That is old school. Now there are, of course, these new ways of looking at things and using prior information about your behavior, of course, which is something I've not discussed so far. But using this type of UCB algorithms, right, each time we see a price for a product from the company point of view, the company is chosen with the option of which price to present to us. And again, this is fictional about this example with airline companies. Search engine, of course, and so on and so forth, going back to the setting of games. Games is not just video games, right? I'm sure you're aware of what happened 5 years ago with application in Go, where algorithms from DeepMind defeated world champions at that game. So Go is a complete game where both players have complete knowledge of what is going on, what has happened in the past. But in 2017, well, the same type of breakthrough occurred in poker, which is not a full information game. So in poker, there are such things as bluffing. The players don't know, right, the cards that the other players have. And arguably, many more situations in real life are closer to poker than to Go, and so on and so forth. Here, another recent example is that of protein folding. So the fundamental question of understanding the 3D shape of a protein given the sequence of amino acid the protein is made of. And well, in 2019, again, an algorithm from DeepMind scored fairly high up in one of the main competitions that is run every 2 years. But in November 2020, they were actually outperforming all the other teams, and so on and so forth. Again, here I've chosen the application of machine learning, staying within this realm, the list of fundamental contribution that have come from a purely statistical way of thinking is long and growing. So I've told you about UCB. I could have told you about stochastic gradient descent, which is by far the main algorithmic paradigm that is routinely used to train modern machine learning neural network type of application. Well, the first paper introducing stochastic gradient descent appeared in Statistics Journal, saying for Q-learning. So the Q-learning is one of the main paradigms to solve reinforcement learning, of which the multi-arm bandit theory is a particular example. So Q-learning is based again on fundamental ideas coming from statistics, Markov chains, so on. Kernel methods, again, fundamentally machine learning. The original papers come from the statistical literature. Again, just a few examples, just within the realm of machine learning. Okay, but statistics is much more broader. There are many other type of applications, and the MathNetStat degree here at Oxford gives you access to both fundamental training, rigorous training in mathematics, and access to that unique way of thinking that allows you to think of randomness in a principled way in order to, for instance, analyze and design algorithms, as I've tried to convey. This being said, thank you for your attention and best of luck with your choice.